Today, we're going to continue looking at integration by parts, our anti-product rule. The integral of u dv is uv minus the integral of v du. We looked at our first upgrade, multiple parts when u is a polynomial. That's bad grammar. Multiple parts when u are a polynomial. And I want to look at another upgrade, which is integrate by differentiating. But before we do that, we want to look at an example. This particular example is going to emphasize the dv choice. This particular example is going to emphasize the dv choice. The idea is that dv has to be something that you can integrate. After you learn multiple parts, this one is a good one to be presented with, because we're really going to be tempted to make u equal x cubed. And then we're going to see that that will not work at all. So our initial thought might be to choose u is x cubed and then make dv natural log of x dx. This might be the first thing that occurs to us, but now we've run into a problem. We immediately run into a problem, and that we do not know the antiderivative of natural log of x. Some of you might. Some of you might know that the antiderivative of natural log of x is x ln x minus x. But for the most part, we don't. If you were thinking of 1 over x, that's the wrong direction. The derivative of natural log of x is 1 over x. The antiderivative of natural log of x is currently unknown to us. So right away, we have a problem. So this choice won't work. We currently do not know the integral of natural log of x. 1 over x is the derivative of natural log of x, and that's not what we need in the dv slot. So 1 over x is the derivative of natural log of x. So we are immediately stopped from this. And this would be a tempting thing to do, because we know that if we put u as a polynomial, then the derivative makes things smaller. So this is not going to work. We cannot distribute our parts this way until we find out that the antiderivative of natural log of x is x ln x minus x. But when we write that for an antiderivative, it gets way worse than what we're about to do. Fortunately, this came from a choice. We were blocked because our choice was bad. All we have to do is go back and choose the other way. We'll just switch them around. I don't know the antiderivative of natural log of x, but I know the derivative of natural log of x. So I'll put natural log of x in the u location, and dv will be the x cubed. Initially, we don't like this because we're going to integrate our x cubed into an x to the 4th, and we don't like things getting bigger. But then we'll notice what du is. So if u is natural log of x, then du is 1 over x dx. If v is x cubed, if dv is x cubed, then v is 1/4 x to the 4th. Now things aren't so bad, because the derivative of natural log of x is 1 over x, and the secondary integral is v times du. One of the x's is going to cancel out. So putting together in the parts formula, I get uv, so 1/4 x to the fourth times the natural log of x minus the integral of 1/4 x to the fourth times 1/x dx. Now, when we're looking at our secondary integral, we can simplify it. So this first term stays the same. We get 1/4 x to the fourth natural log of x minus, I'm going to pull out the 1/4, and this will be the integral of x to the third dx. So our secondary integral is much simpler because when we take the derivative of natural log, it becomes 1/x, cancels out one of the x's. So we end up with 1/4 x to the fourth natural log of x minus 1/16 x to the fourth plus c. Now, when we look at this answer, we could see all those fours running around. We started off with an x to the third, and now we see all these fours, 1/4 x to the fourth, 1/4 squared x to the fourth. So we can go back to our original and replace our x to the third with x to something else. So if I instead replace x to the third with just an x to the n, if we follow the same plan, instead of the 3 being there, the reason we got all these 4s running around is because it's 1 more than our 3. So if I integrate x to the n times the natural log of x, the same stuff will happen. The derivative of natural log will be 1/x. The integral of x to the n will be 1/n plus 1, x to the n plus 1. The n plus 1 divided by the x will leave a 1/n plus 1 times x to the n. And the integral of x to the n is 1/n plus 1, x to the n plus 1. So we can do an infinite number of integrals all at once. There is one case where this will not work. So I've got denominators running around here, so I can't do that. And with those denominators have n's in them. So I can't do this for any value of n because there are some values of n that will make denominators equal to 0. So this will not work if n is equal to -1. So we realized in the previous problem, there was nothing special about 3. It led to all those 4s. 1 over 4, x to the 4th, natural log of x minus 1 over 4 squared, x to the 4th, plus some constant. So if we've got an x to the n times natural log of x, we can just write down what the answer is. Any questions? In particular, this can be used, now that we have this information, or we have a formula for x to the n natural log of x, as long as n is not -1, we can now figure out what the integral of natural log of x is that we didn't have before. So originally we had to switch things around because natural log of, we couldn't put dv as natural log of x. We didn't know the antiderivative. So in particular, if we have just natural log of x dx, I can imagine this as the integral of x to the 0 times natural log of x. And then I could just use our previous result where n is equal to 0 and get 1 over 0 plus 1 or just 1, x to the 0 plus 1 or 1. So I get x to the first times the natural log of x minus 1 over 1 squared times x to the 1. Just by putting n equals 0 into previous results. At this point, we now know what the antiderivative of natural log of x is. It's x ln x minus x. Agreed, that is nice. What that means is that we can now go back and integrate x cubed natural log of x with ln x in the dv slot. This big pause is because I don't really want to do that, because it gets really messy, and this was really efficient. So I'm just going to say, you can now go back to our original x cubed natural log of x and put ln x in the dv slot, and then work out the answer. This is where you would find a very important phrase that you'll see in math books if you actually took the time to read the math book. This is left as an exercise to the reader. That's a math book author saying, I don't want to do it. Yeah, you do it. Any questions? Let's pretend that we didn't know this, because I want to learn this other upgrade called integrating by differentiating with parts. So for the moment, let us pretend that we do not know the antiderivative of natural log of x. Let's just pretend that we don't know the antiderivative of the natural log of x. And we're going to integrate just plain old natural log of x by parts, doing the same thing that we did with the formula. It's good that we know the integral of natural log of x, but we're going to pretend that we don't for the purposes of the exercise. This happens a lot. Next semester, we're going to learn this integration stuff. And I'm going to be saying things like, find the area of this triangle, and not actually care about the area of the triangle. So I'll rephrase the question. Write a definite integral that will give you the area of this triangle. And I'll say, write a definite integral that will give us the area of this circle. And then for those of you who are fancy and come up with just subtraction ones, I'll say, okay, do the one that I'm thinking of now. And then I'll point out that it's you that made this a mind reading exercise. But that's all beside the point. We're going to pretend that we don't know the antiderivative of natural log of x. Pretend to not know. So we know that this doesn't work. We're going to pretend that we don't know. Oops, it's v, not x. Because we're pretending that we don't know the antiderivative of natural log of x, this is still not okay to do parts this way. And the reason that we're going to nope out of this is that for the purpose of this exercise, we're going to pretend that we don't know this antiderivative. But our technique with parts is to just go back and switch them. It looks like we're putting everything in the u spot, but that's okay because there's always a factor of 1, and the dx always goes with the dv. So no trouble. We're going to integrate natural log of x by differentiating natural log of x. So if u is natural log of x, that's bad grammar. If u are natural log of x, then du is 1 over x to x. If v is just 1 times dx, then v is x. Now that we have the 4 parts we put together in the parts formula, the integral of natural log of x, the integral of u dv is uv minus the integral of v times du. Just like with the x cubed, we can simplify our secondary integral to just 1. And just like with the x cubed, our secondary integral simplifies to the original dv that we started with. So simplify the secondary. So we end up with x ln x minus the integral of 1 dx. And the integral of 1 dx is x. So we get x ln x minus x. Yep. And now we know it in multiple ways, which is technically the same way. It's like if you solve using the quadratic formula, you're solving with completing the square. Technically, you just did the same thing. So now we can remember again. Any questions? So this is all very strange. We got one more example today. One of the first problems in the integration by parts section. And we're going to use the same technique. We're going to integrate arctangent of x by parts. And it's going to appear the same as our natural log. The only parts I have available are the arctangent of x and the dx. I can't put arctangent in the dv location because if I knew that, I would just write it down. Now I'd be saying, what's the integral of arctangent of x? If we knew that, we would just write it down. We would just write x arctangent x minus 1/2 the natural log of x squared plus 1. But we don't, so we're going to have to switch them. That's our normal technique. If we tried u is 1 and dv is arctangent, if we knew the integral of arctangent of x, then we'd already be done. So this is not the way. Parts strategy is to just try the other way. Let's make u arctangent because we do know the derivative of arctangent of x. And that leaves only 1 and the dx to be the dv. So the derivative of arctangent is 1 over x squared plus 1. And the integral of 1 is x. The important thing to realize here is that by taking the derivative of arctangent, this weirdo inverse function, it becomes a rational function. The derivative, just like the derivative of natural log, that weird inverse function, the derivative is a rational function. Now that we have the 4 parts, we can put these together in the parts formula. So we're going to say the integral of uv is uv minus the integral of v times du. In the natural log of x problems, we were able to then simplify our secondary integral, but that's not available here. X over x squared plus 1 is already simplified. The degree of the numerator is less than that of the denominator. This is already simplified as a rational expression. But since we have x on top and x squared plus 1 in the denominator, we can integrate this by substitution. So in this case, our secondary integral is substitution. W is going to be the x squared plus 1. So dw is 2x dx. So 1/2 dw is x dx. So this x dx on top will all be replaced with a 1/2 dw. And the 1 over x squared plus 1 will be written as 1 over w. So now we have to integrate 1 over w. Since the derivative of natural log of w is 1 over w, the integral of 1 over w is natural log of w. We can't leave our answer in terms of w. The problem is stated in x. We have to answer in x, but we just need to replace the w with our expression x squared plus 1. Note that when we integrate 1 over w, we get natural log of the absolute value of w. That's to make sure our domains match up. But when I replace w with x squared plus 1, we can note that x squared plus 1 is always positive. And so I don't have to worry about the absolute value symbol. The absolute value of x squared plus 1 is just x squared plus 1. X squared plus 1 is always positive. Unless x is complex, which it is totally not, because this is real analysis. Oh, sorry. This is elementary real analysis, so it's calculus. This problem shows up in 3 different ways. Number 1, I just do the problem as part of the lecture with this integrating by differentiating thing, and we use parts. Number 2, it shows up on the homework, in which case half of you look it up, and then the other half say, could you do problem number 2 from the homework? And I'm like, oh, sure. Then it just becomes a problem that I go over in class as part of the lecture. And number 3, I put it on a quiz, which is the most fun. And like some of the students that have been through the class before and remember it, like, oh, I got this. That's like 2 of them. Get the problem, and everybody else is like, oh, I don't know. Then you just like guess. It's kind of awesome. You put like arcsecant and stuff. It's pretty cool. Creativity goes through the roof when I just put it on as a quiz. Correct answers do not, but creativity is like spot on. It's really great. It's also when one student's like writing something complete nonsense because they're just like desperately trying to write stuff, and then some person is copying off them and they write the exact same complete nonsense. I'm like, oh, dude, you cannot copy exactly a random string of letters and people believe that you did not just copy this random string of letters. You know what I mean? My favorite instance of copying happened when I was teaching high school. And the thing is about high school students, they are terrible at cheating. But what's funny about high school students is they think they're good at everything. So they think they're good at cheating. Now, it wasn't too much of a problem, except the two guys that were cheating off each other. First of all, neither one of them could do any math. I was having a very hard time trying to fix this because they were fighting me. I'm like, oh, learn some math. I'll make it easy for you. And they're like, oh, no. So the copying was rampant, but neither one knew how to do anything. So it wasn't really a problem, except for the fact that one of the dudes wrote his nines, not like this, but like this. I don't know where he picked this up, but he wrote his nines in this fancy way. Now, yup, wouldn't have been a problem, except like, as I mentioned, they weren't really good at being students. They didn't listen to me. So when I told them, don't write in all caps, they didn't stop writing in all caps. So person B, who wrote in all caps, looked at weird number 9 dude, saw this and wrote G. So when person A wrote like 97, person B wrote G7. I'm like, oh, dude, that is my favorite instance of cheating in the history of my teaching career. Weird 9 guy and all caps guy combining together. They're probably engineers somewhere. All right, that's all beside the point. So usually I try to do more creative ways to introduce the integral of arctangent is x arctangent of x minus 1/2 natural log of x squared plus 1 plus c, but it usually comes down to me just doing the problem anyway. Also, if I just leave it to office hours by not doing any class, then I just have to do the problem like a dozen times. People like come by my office hours. How did you do problem number 2? I had a question on problem number 2. I had a question on problem number 2. And then the next day I just do the problem. You know what I mean? Because I like factor out. Some people would be like, oh, well, that's just being a lazy teacher. I'm like, oh, yeah. The whole point is to be as lazy, to do maximum lazy. You want a maximum lazy so that you can do minimum work. This goes for everything that you do. Everybody's like, oh, you have to work hard to be successful. It's like, oh, no. You have to do as little work as possible and get shit done to be successful. Because if you're lazy, you are going to put your effort into finding efficient ways to do things. So find an efficient way to do things so you can have more time. This is especially true if you're not being paid by the hour, you're just getting a yearly salary. And you're expected to work a certain number of hours. The only thing that you have control over is the amount of effort that you're going to put into it. You should minimize that so that you maximize your dollars per unit of effort. Your dollars per unit of time, that's kind of fixed because the boss says you have to come in 40 hours per week, and this is what will pay you to do that. I go, but I don't have to do work for all 40 of those hours. Do that. Minimize that. Exactly. You want to maximize dollars per unit of effort by minimizing the units of effort that you put in. This is how you play the game called capitalism. If that's the game that we're going to play, that's what you have to accept. You know what I mean? And if your company is like, oh, we're a family, find another fucking company, because that is bullshit. Because they want you to believe it's family. So when they ask you to come in on the weekends and sacrifice your family time, you think it's reasonable. That's unreasonable. Punch up your resume and punch out of that company. You know what I mean? Yes, companies, I am telling all of my students that, and I'm hoping that it lands. I want them to minimize the amount of effort until you give them some fucking respect. Do you hear me? I'm looking at you, billionaires. We could do this the nice way, or we could do this the old-fashioned way. All right. That's it for today. I will see you all on tomorrow when we do some integration by parts training. Everybody have a good day. Thanks for playing.